Electric vehicles are hardly a new thing, but climate change and dwindling non-renewable fuel sources has created a pressing need for governments to incentivize the large-scale adoption of affordable alternatives to gasoline combustion engines. Understanding the principles of Voltaic cells precedes the development of battery technology, so that the best combinations of materials can be found to produce the most efficient anode and cathode pairings. In this investigation, we shall be using 8 different metal strips and 8 test tubes containing the ion solutions of these metal strips. A flexible tube of potassium nitrate gel will serve as our salt bridge. In part 1 of this investigation, we will create our own table of reduction half reactions based on the measured potentials of a variety of metals in their metal ions, using a nickel electrode and a nickel 2 ion electrolyte as a reference half cell. For the first test, the nickel-nickel ion reference half cell is paired with a magnesium ion electrolyte into which a magnesium metal strip is inserted. A salt bridge containing potassium nitrate connects the 2 half cells. A voltmeter connects the metal strips, the electrodes, of the 2 half cells. We immediately see a voltage reading, however the voltage is negative. Voltaic cells should have a positive voltage, so we switch the voltmeter leads to make the voltage reading positive. In this lab, we see the red lead is the anode, where the electrons flow into the voltmeter. The black lead then is attached to the cathode, where the electrons flow from the voltmeter. In data table 1, the metal-metal ion pairing for this first test was magnesium metal in a magnesium ion electrolyte. We identify which electrode was the anode and which was the cathode. We record the reading of the voltmeter as the measured potential of this voltaic cell. After rinsing the salt bridge with distilled water, we switch the magnesium ion half cell with a test tube containing a copper 2 ion electrolyte, into which we place a copper metal electrode. We repeat the process, recording our results as we go. The third test involves an aluminium electrode in an aluminium ion electrolyte. Which voltmeter lead connects to which electrode depends on which combination produces a positive voltage. Remembering to rinse the salt bridge between tests, the fourth test connects a tin ion half cell to the nickel ion half cell. The fifth test, an iron electrolyte solution with an iron electrode, connects to the reference half cell. The sixth test connects a silver ion half cell. The last test, a zinc ion solution with a zinc electrode, is connected to the nickel ion half cell. You now have enough data to complete the first problem in the analysis section of the investigation, creating a table of reduction half reactions. In part 2 of the investigation, we'll create a voltaic cell by connecting the aluminium-aluminium ion half cell with the tin-tin ion half cell. Before we apply the voltmeter and using the information in the table of reduction half reactions you created earlier, record in data table 2 your predictions of which electrode would be the anode and which electrode would be the cathode. Calculate the cell potential from your table of reduction half reactions and record it in data table 2. Record also the cell notation for this voltaic cell. Connect the voltmeter in a way that reveals a positive voltage. Record this value in data table 3. Now you have enough information to complete the analysis section of this investigation.